all the JNANAM team members to continue to stay here. We will shortly start our first session of the workshop on nanosatellites. There is a slight change in the earlier schedule that I had given. So the first session of today's workshop is going to be on physics of satellite motion, basically the orbital dynamics, and this will be delivered by our advisor on the JNANAM project, Dr. S. Rangarajan sir. Before it starts, I will just give you a brief introduction about Dr. S. Rangarajan sir. So Dr. Rangarajan sir has more than 40 years of experience in the satellite industry. He is a former director of ISRO INSAT program as well as ISRO at Hassan. He is also Chief Technology Officer at YASMI USA, and he's been involved with many space education activities across the globe, in fact. So in India and in countries like Africa and many other third world countries, he has his own satellite application to deliver education to remote areas without internet. So he also delivers talks at various platforms. He's a very eminent person with an in-depth physics background, with plenty of publications, honors, recognitions, and awards at United Nations, World Bank. He was a guest faculty at UN Center for Space Science and Technology Education. He's a member of committee that drafted the National Telecom Policy of 1999. Is chairman of Board of Studies of Mysore University's Space System Management Award from the Astronautical Society of India. He's a winner of J.C. Bose Award. Okay, so and many more. So because of short of time, I will not get into all the award details. I request Dr. S. Rangarajan sir to take over the platform to deliver the first session on the physics of satellites. Thank you, sir.
Thank you, Dr. Sudarshan. And I would want to share my screen. I'm just wondering what would be the best way we'll do it. Stop presenting, it says. Can you enable that for me, please? If I say the entire screen, it's not showing up. Share your entire screen. I think you have to enable that for me, please.
It's enabled.
Because it's
Yeah,
not.
I think it's enabled, sir.
But why it's not allowing me to share? I want to say share, it's not coming up. Let's see what I should do for that. I cancel.
Stop sharing.
The share part of it. Okay, maybe a window, but window is not good.
Yeah.
If I take a window, it will not give me the full
Just
screen. Okay, start with the window.
Stop sharing and start sharing. Repeat that process.
See, now
Yes,
you may be getting, but this is not the full
yes,
screen.
sir, we got it, sir. We got
Do
it.
you get the full screen? Let me see.
Yes, sir.
Good. Are you getting the full screen mode?
It's not in the full screen mode.
Sir, this is Shankaraya.
Yeah.
Go to presentation mode, sir.
Presentation mode.
There is a one icon.
Stop sharing. Shankaraya?
Yeah, it's shared. It's shared. Go to presentation mode, sir.
Where, but I don't have any other option.
I think it is in the another tab.
Because it is in a window. If I take the full screen, it will give me that, I know. But then it wasn't allowing me to share. Let me see. I'll go once more. We'll try once. Otherwise, I can. 1 minute. Stop sharing. Are you seeing the screen?
No, sir.
No. Okay, let us go
Yes,
back.
yes, sir. You have to select the tab which has full screen.
Okay, let us go back to close this. Okay, no, not close. I can, let me, sorry for the small pitch. See if I go back here. It gives me three options: your entire screen, window, or tab. Should I take tab?
You can take the window which has the full screen.
Sir, entire
Multiplication.
window.
Entire window.
Okay,
Entire
entire is also fine, sir. That's it.
mail. Okay, this is not there. Cancel. The entire window. Let's try. See, a window is there. Your entire screen. Yeah, let's take
Yeah.
entire screen. But if I
Yeah.
take entire screen, share option is not coming. It says only cancel is. Chrome wants to share the contents of your screen with Meet.
Yeah.
It says that, but it doesn't allow me to click on share. I don't know why. No, entire screen. Okay. Click on the screen. Okay. Click on the screen. It will give. Okay. Now it came, but my screen. Now it's you are presenting your screen to everyone.
Yeah, now it's fine, sir. Only
But does it show me the slides? Let me see. Where are my slides? But slides are here. Okay. Okay. Now, if I go to this one,
Make it a full screen.
full screen. That's it. Are you able to see the full screen?
Yes, sir.
yeah.
Excellent. I'm sorry for the little gap. First of all, a very hearty welcome. I am very proud to be part of this special team. It cuts across disciplines, cuts across geographies, and even hierarchies. And in order to provide an induction course to you, we are very proud. I'm doubly happy because for the first time in the last 40 or 45 years, my talk is called Physics of Something. Though I'm a physicist, I've been over the years working in so many different disciplines, and very happy to see that I'm back to physics, because which is central to many concepts. So I'm not going to give you a physics lecture if some of the students wanted to avoid it. It's going to be definitely more exciting. In fact, I'm very happy about the diversity in your presence in the audience, which is our great strength. Because cutting across all these disciplines, when you work as a team, you produce something very unique. As Dr. Mahadev Swami has been repeatedly mentioning, your passion, your commitment, your dedication, etc., are very important, because we are really talking about an extremely time-bound project. It can be done, we will do it, and that requires that you give us highest priority for this. So let us proceed by going into that. And also interestingly, the JNANAM part of it, which is a very, very appropriate name when it comes from out of the JSS group. I wanted the first mission to be the A is application, M is medicine, and that is even better than generally talking about atmospheric sciences, atmospheric methods. Now let us move on to talk about where we are today. At this juncture, space in India as well as space abroad is in a very critical stage. It's undergoing a transformation from government-funded agencies to the private sector supported by the government. It's something very unique. It happened everywhere. In the United States, it was NASA only, but over the last couple of years, you hear more about what Elon Musk does in the space sector and so on. It happens everywhere. And in India is not lagging behind. We also realize that for all the investments that we have made, 50 years ago when I was, we were all in the beginning of this space sector here, we had to fulfill Vikram Sarabhai's dream, where the main interest was to use this unique technology for societal benefits. And so the government invested on this vision, and it has really produced extremely good infrastructure. We moved from the experimental stage to the operational, to the commercial stage, etc. But now this mode must give way to a large number of private players, private companies, everyone for that matter should be able to be having a role in this very exciting field as it is developing, exploiting the infrastructure, making profits, and still continuing to provide the benefits to the society. Government has a role to play. It is more in terms of the legalities, in terms of making sure that the exploration of the distant part of the universe, all these probably will continue with the governmental agencies. But primarily, the activities which are leading to societal benefits will get passed on to the private sector. When you look at this, a sample even, I mean, it's an extremely small sample actually. When you look at space, it has tremendous potential in terms of tapping, for example, energy sources. Energy is such an important thing, and we are finding lots of shortages. And it's going to be not too far in the future where we will be able to get any amount of energy from the sun properly transformed and delivered to the ground for supply. Or mining, there is another very exciting kind of field. Or maybe in terms of scientific experiments, you have a better place to conduct experiments. As today also, the Joint Director explained how the biophysical experiments would be able to be you can grow some cells, you can grow proteins, etc. in the space conditions and be able to later replicate things which could not have been possible if you want to do everything terrestrially. And there are other exciting things like debris. Debris on one hand is bad, you have to remove it. But on the other hand, you can repurpose it. There are very interesting ideas which are floating around, and there are going to be projects like that. And there are ways by which you take the water from there, you get the oxygen and hydrogen, use that hydrogen for some other purposes in the space sector itself, like this. Manufacturing as well as research will get a big boost if you are going to expand into the outer space. And also, as Dr. Kalam always used to say, one of the biggest gains in terms of the technologies which were developed for the space sector was in terms of providing something very unique for the needy in the health sector and all that. These are the kinds of ripple effects. Essentially, I believe that this will transform the blue planet of ours to green. Why do you suddenly think that the space opens out so many opportunities? Newer avenues, why do they come? That is mainly because, firstly, it gives you a global perspective. When you look at the camera which is looking at the Earth, but mounted on the satellite, you get a panoramic view which wouldn't have been possible from cameras which are, even drones cannot capture that kind of a view. And that is also useful for navigation purposes, because otherwise, today we take that for granted, that you get the GPS signal, tells you whether you should take a right turn or left turn, or where is your destination, in how many meters. That's all possible because of a set of satellites like the GPS, or more recently, the Indian version of that, which was used, Gagan was used in terms of even in the aircraft landing. The other important characteristics of space is in terms of the fact that it's above the atmosphere. So therefore, for astronomy, for example, they are jumping at it. You have a vision which is never possible from a ground-based telescope, because the atmosphere and the scattering involved makes the vision not as good as what you would get it with a telescope which is abroad. All of you are familiar with whatever has been happening globally in terms of, for example, the Webb telescope, which is so far away and it's going to produce so much of information about the outer galaxies. The other interesting fact about the space is the microgravity, which is important for manufacturing or experiments of that kind. And like this, of course, of all the things, I always like the fact that the one-to-many delivery, which is how the DTH kind of television delivery started in almost globally. Now it's going in for delivering alerts, delivering educational contents, and so on, so that you get an equitable reach everywhere. But it's very, very important to analyze the needs and then develop around that, rather than just be driven by the supply. So when you look at the mission, broadly, we talk about the space segment, which consists of the orbit and the satellite. Then you have the ground segment and the user segment. The ground segment, you can have the provision for controlling the satellite or collecting data from the satellite, the telemetry, telecommand, and all that. And also the user segment, where the user agencies get the specific data from the satellite, and that is converted into information which is delivered to the final users. And that gives you the knowledge part of it, the jnanam. So it's very appropriate that ultimately we do all this because there's going to be definitely a benefit of that kind. And space is unique, and space can be made use of in this manner. But then this cycle, if you look at the mission elements, you have all kinds of things. This is for a big satellite to small satellite. You'll have users, because without users, why do you want to spend money? Even if it's 1 crore, it's a lot of money. But then it has to have a launch. I will explain why a launch segment is required. That it's in an orbit, the satellites are something which go around the Earth. Then you have a variety of other things like the control center, or in terms of the user segment, data processing, and so on. But what is common to all the satellites is the fact that there should be a launch vehicle. What does the launch vehicle do? Here I have taken, for example, the PSLV, which is one of the workhorses of India. We have launched more than 100 satellites in one launch and so on. It's a very remarkable kind of a thing from Sriharikota, where we have the launch pad. We have this PSLV able to take the flight. You look at this diagram. I don't want you to understand all of it. The whole idea of giving this talk is to make you familiar with the terminology and be in a position to ask the right questions and be able to see the big picture. From that point of view, look at this fact that the PSLV has got 4 stages. What is meant by stages? When a rocket is there, by burning a fuel, can be solid or liquid, it propels itself, it moves. For example, when it takes off, you've seen that it goes vertically up and so on. So that is what is called the thrusting part, because the fuel is burnt and then it starts giving the momentum to the rest of the body, and therefore it starts getting an additional velocity. But then not all the time it keeps thrusting, because the moment it has acquired some velocity, the physics part of it says that it will continue to move. Maybe it will decelerate, but it will continue to move. That is called coasting. So you combine the thrusting part and the coasting part alternately. You have in fact 4 stages. So first stage burns out and then it goes for a while. Second stage starts and burns for additional time. It gives you additional thrust and then coasts again. So in this whole process, what we ended up with is, if you can see the right hand side, it shows the display, and I'm sure some of you might have seen during the TV broadcast of these kinds of launch missions. The red dot shows where it started from, that is in the eastern coast of India, in Sriharikota. And then you see a line which is coming southward. That is how the rocket's path, as projected on the Earth, is moving. And you see that it's coming down. It has avoided Sri Lanka and all that. It goes all the way and passes through the equator. And in fact, if you see the numbers below, you notice that in less than 20 minutes, it has achieved an altitude about 500 kilometers. In fact, we are talking for JNANAM about 500 kilometers. We have reached that kind of altitude. And it has got a range that is from Sriharikota. It's already traveled 6,000 kilometers. And another interesting point is, when it crosses the equator, it was not vertically down nor horizontal. If you look at the correct angle between the plane in which it's moving and the equatorial plane, it's something like 97 degrees, almost 90 degrees. So because it's a polar, the P part of it is a polar satellite launch vehicle, it gives you what is called a polar orbit. I'm going to talk more on the orbits very soon. So therefore, you notice that a launch vehicle essentially has a short duration mission, 20 minutes maybe. But within the 20 minutes, it takes the satellite to the correct height as well as imparts a correct velocity. Velocity is the vector which has got the direction and the magnitude. It has to give the right magnitude and the right velocity. And that is what is the purpose of a launch vehicle. So which means that once you have a launch of that kind, the satellite will continue to keep going round and round the Earth just because we have established the right initial conditions. Look at this little simulation. You notice Earth is rotating. Now the satellite is coming over eastern part of India. And then in the next revolution, it's coming to the central part of India. And after some time, it has already gone over the Middle East. It's no longer over India and things like that. So the kind of circle which is shown there is the orbital path as well as what the satellite can be able to view if you have a remote sensing mission, what kind of regions can be photographed. So you notice that this motion which takes place, it takes typically about 100 minutes if the altitude is about 700 kilometers. So this is the first part we understood. Then immediately it throws open a very important question. Why does it keep moving? Why can't it fall down? Because, people ask this question. In fact, I was very happy in the last session, which we had about a month ago, the same group. One of the girls from Noida was talking about how her IIT-K friend had talked about, oh, it's moving at 8 kilometers per second, blah, blah, blah. But now, after today's lecture, I presume you will be the expert. You will be able to talk on that kind of language to any of your friends and share this excitement. What's happening is, when you ask the question, why doesn't it fall down? In fact, you're asking the wrong question. For example, even take the smallest thing, like any child knows that if you take a ball, the ball, if it's dropped from the table, it will fall down. So you think, okay, gravity is pulling it, it falls down to the floor. So this is the correct phenomenon. But if suppose somebody asks a question, if I throw the ball up, will it go up or go down? It will go up first and then only it will go down. But people who are thinking that something, gravity is pulling it and it is to go down, will say that, how is it going up? It all depends on how you start with. What is the initial condition? That's why I've shown the little mount like that. And then you would have studied in your college level physics course, projectile, a trajectory of a projectile, a parabola and all that. What it shows is that if you just drop the ball, yes, it comes vertically down. But if you throw it horizontally, it would probably go a little farther and fall down. If you give a little bit more force, it will go even further out, etc. Like when the cricketer today, it's all IPL is almost every day people keep watching games. You see how and which angle the batter is able to hit the ball so that it goes all the way. One guy did 117 meters or something like that. He was able to get that range because of the physics involved, at what angle it has to take off. And then despite the gravity pulling it down, it should not come down and fall in the hands of a fielder. It has to clear all those fielders. And that was possible because of the initial conditions that the batter gave. Here, the initial conditions are given by the launcher. The launch vehicle gives you the initial conditions. So the initial conditions, what we are talking about for the velocity, for that purpose, let's first understand, actually, these are all coming under what is called Newton's second law. The second law says that any body which is acted on by an external force gets accelerated. Acceleration is force by mass. The acceleration is a vector, velocity is a vector, position is a vector. The acceleration is the derivative of the velocity, dv by dt, which it does is a d squared r by dt squared. It's a second derivative. So therefore, if you want to find the position of any object in a two-body problem, that means you have Earth and the satellite, you are having a two-body problem, a second order ordinary differential equation for the vector r is required. If you solve it, you know the r forever. You can find out where it will be at different times. After 1 year, where it will be. After 2 months, where it will be. 2 minutes, where it will be. All are contained if you know what was the position and what is the velocity at time t equal to 0 when you start. So when you want to start, you have the position, which are 3 components, velocity, which are 3 components. Totally 6 scalars will totally define the orbit. One orbit and another orbit differ by only the 6 parameters. The 6 parameters are going to be conveniently shown geometrically by a Keplerian method very soon. But first get a feel of it. What all makes it go round the Earth is because there are 2 different phenomena. One, the gravitational pull, which is toward the center of the Earth. Rather, the tendency for a body which has got a velocity to continue to move along the velocity vector. So if the gravity is switched off, it would have gone straight tangentially outward like that. Whatever is the velocity, nobody can change the velocity, and therefore it will just continue with the same direction, the same magnitude along that straight line. But now here it's curving and coming around and orbiting is because the bend is because of the pull of the Earth. It's so easy to understand. Don't bring in all the centrifugal force, centripetal force. Nothing is required. How much it bends is decided by how much you pull. And if you have the right velocity and the right amount of pull, the amount of curvature will beautifully match the Earth's curvature and you get a circular orbit. That's what we are trying to show there. And we have very specific questions. Of course, the orbital elements, let me first explain. That is basically you have the orbit, which is defined by the initial position, initial velocity. Those two will define a plane. So the motion is entirely in a plane. The plane is something which on that only the satellite moves. So the path can be expressed in terms of the orbital elements. Let me try to give you the example. I have tried to put it here, not so much for you to learn all these terminology. Basically, it's general information that the motion of any body in this two-body approximation is in an elliptical path. Elliptical path has two parameters. What is the size of it? That is the A, the semi-major axis, and eccentricity, which is showing how oblate it is. That is, if eccentricity is zero, it's circular. So the eccentricity will denote how much it deviates from being a perfectly circular orbit. So that is A and E. That defines the shape of the ellipse. But then I told that the orbital motion is in a plane, right? That plane has to be correctly described. To describe the plane, we give two parameters. How inclined it is with respect to the equator. That angle I, which is shown here, is showing what is the inclination of the particular plane. This plane, how is it? This angle is I. Then the second one is this plane and the equatorial plane cut here. How much is this cutting point? Where is it in the equator? We don't give it in longitude. We give it in a very funny kind of an angular coordinate called the capital omega. Don't worry too much about it. Then on this plane, you have the particular ellipse. So we have taken care of two parameters to define the plane, two parameters to define the size and shape of the ellipse. And then we have to orient the ellipse inside the plane. That is given by a parameter called small omega, it's shown here. If you look at it, this parameter, which says where is the perigee. Perigee means where is closest to the Earth is called the perigee, and that is closest point to the Earth. And that where does it occur with respect to the point where it crosses this equator. So that is the small omega. And finally, with respect to perigee, where the satellite is, that is the angle called true anomaly. In fact, when I first started on this subject, I was also amused. Why anomaly? Anomaly and such things are usually having a different connotation in our normal usage. And I was wondering, why do they use all these funny kind of thing? It looks a lot of Greek and Latin to me. Yes, it is. So what? We don't have to worry about small omega, capital omega, and all that. But you must know that there are only 6 parameters, whether you call them as the 3 components of position, initial position, 3 components of initial velocity, or 6 Keplerian elements. It has to be only 6. And some of them will be 0. When you take a circular orbit, it will be 0. Equatorial orbit, inclination will be 0, and so on. I'm going to show some of them by a very clear animation, because nothing like viewing something. The orbits are classified in terms of the inclination, how it is oriented, how the orbital plane is oriented with respect to the equator, altitude, how far away you are from the Earth's surface. Are you very close, 500 kilometers, 1,000, 5,000, or that is the altitude, the height, and the shape, what kind of a circularity, or is it elliptical, and so on, and what applications could be used. Let's take this first types of orbit. If you base it on inclination, you can certainly bring in, this is the equatorial orbit. That means the small box which you saw was going around horizontal plane, which is on the equator of the Earth. Let's, once you see some more pictures of that, you'll know what is the typical thing. Now it's an inclined orbit, typically like 45 degrees inclination. And in this, let's see the movement. The movement will be, it goes up, goes all the way, comes back like that. So this is how a revolution takes place. It's called the inclined orbit. What happens if the inclination is increased all the way to 90 degrees? Then we call it the polar orbit. That means the satellite goes to the North Pole, to South Pole, to North Pole, South Pole, like that in every revolution. And here the movement will be like this. It cuts the equator in two places. One is the ascending node, north to south, descending and south to north to south, and here south to north. And let's see, one last of the categories is called retrograde, where the inclination is even more than 90. In which case, the Earth's rotation is in one sense, west to east. This goes the opposite to that, and that is called the retrograde orbit. So these are the types of orbits which could be there. In particular, if you look at the variations, the different orbits in terms of their distance from the Earth, you call them LEO, L-E-O, low Earth orbit. In fact, about 10 years ago, if you asked LEO, nobody might have even known what is a LEO. 10 years from now, or even 5 years from now, almost everybody will know LEO, because the way this low Earth orbit is going to be filled up with satellites, with constellations, like, for example, many different companies providing their own constellations. You have constellations provided by the Elon Musk, I told you, Starlink, or you have one of the India and with partners abroad trying to provide OneWeb and things like that. All of them have thousands of satellites in low Earth orbits. And then you have intermediate circular orbits, the geostationary orbits, and so on. But if you look at the motion, you see how they are all moving around. They go at different speeds, okay? Because the period in a LEO is typically like 100 minutes, we saw. In a ICO, the intermediate circular orbit, could be 6 hours, 8 hours, and so on. And the GEO, which is geostationary orbit, is very special, and it has got a 24 hours kind of period. I'm going to show that very specifically to you. Like, you look at the GEO. Here, what happens? The Earth rotates one full round in 24 hours. That's why we get the day and night, because all the stars are stationary and the Earth is rotating. And so apparently we see the sun rising, sun setting, and again sun rising 24 hours later. So this 24 hours is the period for Earth's rotation around its axis. If the satellite also has the same period, then you see how beautiful the red dot is. It looks as though it is attached by a rod to Earth. So therefore, if it is over, let's say, Indonesia, it will continue to be over Indonesia forever. After 1 year, after 3 years, after 10 years, it will be over. If it is over India, of course, it's normally on the equator, it's equatorial plane, and on the equator, you see that it's over 74 degrees, which is over central India, and you will see that it will be always at 74 degrees east. Its period is matched, and it's 24 hours. And this is exactly what was predicted by a gentleman called Arthur Clarke, even 10 years before the first satellite was ever made. He wrote in a scientific magazine saying that these platforms will be very useful for relaying signals across continents. A signal which is sent, let's say, from India could go and land up in London and so on with just one hop, because of the fact that these are very far away. So each one satellite here will cover 1/3 of the Earth. So this is very popular for telecommunications, broadcasting, and so on. So the geostationary orbit or geosynchronous orbit. Obviously, we are not going to use it for JNANAM. We'll use one of those much nearer orbits. But you should know all this, because once you say that I'm working on a satellite project, people will come and ask you, do you know what is this INSAT? You should be able to tell them. So let me summarize it very quickly, because we have talked of so many things here. You can classify the orbits based on the inclination as equatorial, where inclination is 0. Inclined orbits, it could be any, it can be 30 degrees inclination, 45, 67, 80, 90, like that. 90 itself is very special. We call it polar. Anything around 90 also, like 97, etc., we still call them polar, because they've got some other interesting properties. They become what's called sun synchronous for remote sensing satellites, where you want the ground illumination when you image to be identical for comparison of images. You use a slight higher inclination than 90 degrees. So that kind of thing. What about classification by altitude? Altitude, you can LEO, which is the low Earth orbits, then intermediate circular orbits like our GPS orbits and so on. Then you have geostationary or GEO also, they say sometimes. And in terms of the sizes, shapes, you have circular, elliptical, which are very common, of course. Parabolic is basically hyperbolic, or not really orbits, because they are open kind of surfaces. So they are used for going outside of Earth's gravity, escaping, and then going to, let's say, moon or going to Mars and so on. And that is very much possible if you have that kind of a capability to go around like that. That is in terms of the shape. Applications, of course, are plenty of applications. Just very broadly, remote sensing, which is meaning that you use the satellite with its imaging facility, a camera, and that could take images of the Earth. Today everybody talks about selfie. So Earth takes a selfie from the camera which is mounted on the satellite. The advantage of this selfie is that this is very systematic, because the orbital motion is predictable, and so it would go over the same places as predicted. It would come over there, and so for the pictures can be very nicely interpreted geometrically. The other advantage that you get is the large coverage area. Because of the height of the satellite, it will be able to simultaneously be able to view large portions of the Earth. That's very useful for remote sensing. Today, for example, some cyclone is coming up in the Bay of Bengal. All of us keep following the images which are taken by the satellite, and these are taken in, let's say, visible, or can be taken in thermal infrared, and those are processed and presented to us so that we'll see the eye of the cyclone, how it moves, because every half an hour we take an image using one of those payloads which are there in INSAT satellites, and we use that not only for ourselves, to the neighboring countries. So the other important part, the remote sensing need not have to be only limited to imaging for pictures. It can be remote sensing in any of the electromagnetic frequencies. It could be for radars, it could be microwave remote sensing, and so on. Communication is to use the satellite as a platform to relay a signal and connect two terrestrial points. You could communicate across continents, as I was mentioning, or it could be over small regions also. Instead of using a tower which is let's say only having a reach of 5 to 10 kilometers, you can have this tower which is much higher and be able to cover larger distances. That is where the communication LEO's constellations come into the picture, because they believe that they can reach out to any part of the globe. For example, rural part where you want to go and work from home, you want a high quality, good internet, and they believe there's a good demand for that. Navigation is again a very important application, where you find out the position on the ground by looking at the signal as received from well-defined satellite constellation. GPS has 24 satellites. So at any time, if you get 3 or 4 satellite signals and process it to find out where you are. So you know the positions of the satellites and you don't know your position, you calculate. It's a simple mathematical calculation. You use for surveillance, of course. You notice during the war times how people keep looking at it, and lots of applications are there, which are all for the tactical applications, for the defense, and that's all the types of applications. For example, if you want to find out the emissions which are coming out over the region, and very quickly you can locate it. Geolocations, all these possibilities exist. So in terms of summary here, you notice that you have missions which could be in low Earth orbit, intermediate circular orbit, or it can be geo or beyond. It's not at all limited to this. You have Molniya orbits, which are used by the Russians because their coverage is all at high latitudes, and therefore they want a different type of orbit for that purpose. And typically, you notice there is a relationship between the size of the orbit, the semi-major axis A, which is shown here, and the period of the orbit. These two are related. Exactly like for example, suppose you take the solar system, you have the Mercury, Venus, the Earth, Mars, and so on. As you go to larger distances, the period of going around the sun keeps increasing. This is Kepler's third law. T squared is proportional to A cubed. Exactly what happens here also. At 750 kilometers, you have 100 minutes orbit. When you go to 35,000 kilometers, you have 24-hour orbit, like that. So therefore, the applications correspondingly change. When you come to the low Earth orbit, you must understand, because of the 100 minutes or 90 minutes period, the Earth is continuously rotating. And therefore, over 100 minutes, it rotated 25 degrees. So therefore, in the next orbit, first orbit, suppose it is going over the eastern part of India. After some second, then the very next orbit, it will cover the western part, and then it will go further to the west of India. And then you have to wait for another set of 2 passes, which would appear when it is going from the previous ones were south to north, means north to south. You will have 2 more passes like that. So that's a kind of visibilities which we will discuss next. So the orbital events. Why do you want to study orbit? Because it's the orbit only. Once you have chosen it, it's fine. You reach that with the launch vehicle, it puts you into that orbit. But then once you have the orbit, you know how the behavior will be, because everything is very systematic. The things which are when, at what time the signal will be available for you to track, where you can get the data from the satellite, when the satellite will undergo an eclipse, means the shadow of the Earth falling on the satellite, stopping the generation of solar energy, and all these other nodes and all that, ground tracks, etc. We'll talk very briefly. So in order to do this calculation, it really is a lot of math. Don't worry about the mathematical part. It doesn't matter so much of jargon. But what is most important to note is, if you look at a station, and if you say that a satellite is visible, it should come above the horizon. See, exactly like when sun is rising and then it goes over and then it sets, same way the satellite also will come above the horizon. It's called the elevation angle. If elevation is 0, it is at the local horizon. If it is more than 0, it keeps becoming visible, continues with highest elevation, whatever, say 40 degrees, 50 degrees, like that, and then it can come back, reduce the elevation, becomes again 0, and then that is setting. So in that portion of the orbit, it is visible. Visible means not to the eye, it is radio visible. You can get the signal from the satellite to the ground using antenna, using electronics, which will be available as a ground station. So therefore, that part of it is very important. The only other parameter which is here is what is the distance to the satellite, and the distance factor is basically called rho here. That is the range vector, and that is what gives you the concept of how many kilometers, like we saw 6,000 kilometers to that. Even though the orbit altitude may be 500 kilometers, you may be able to receive the signal when it is 2,500 kilometers from the Earth station, because it's at a slant range, which is what is indicated here. The next point which you understand is this concept of shadow, because the shadow is very important from the point of view of power balance. Because when you talk about power generation, it requires sunlight, and Earth's shadow falling on the orbital path will make that unavailable, which means like you have to use a storage device like the battery to provide you power for the essential units. Some of the non-essential ones may be switched off to save the battery usage, and later when it's sunlit, the battery will be again charged. So you have a rechargeable battery which stores the energy and be used during the path. But then again, it depends very much on the type of orbital geometry, how the angle, relative geometry between the sun and the orbital plane is what governs this eclipse. For example, suppose you have a polar orbit, and if the equatorial crossing time is at 6 a.m., then what will happen is the 6 p.m. will be the other equatorial crossing. The sun's rays will be always perpendicular to the orbital plane. So it hardly will experience any shadow. So there won't be eclipse. Almost the entire orbit will be sunlit, except in some few seasons because the sun's rays will be a little bit tilted from the equator. So otherwise, this is a very important calculation. At least you should know the eclipse is a number which you should worry about for power calculations. This also is for just tracking. When the previous slide I was talking about how the range vector and how above the horizon it comes, we talk about the angles. Here you see if you look at it from the ground station point of view, there will be an antenna. Okay, these antennas are looking at the satellite. Of course, nowadays we have almost at every home there is a DTH antenna, Tata Sky or Sun Direct and so on. Those antennas also don't track. They are always pointed in the same direction. That is mainly because they are all connected to a geostationary satellite. So relatively, the satellite looks as though it is not moving. Please note, every satellite has to move. If it is not moving, the satellite will just drop down dead straight vertically down to the center. That it is not falling down means it's moving. But why does it look stationary? That is because its movement is matched with the Earth's rotation. And such a satellite, therefore, tracking is very easy because once the antenna is pointed towards that direction, it is always in that direction. Even sun, moon, etc. look as though they are all moving, whereas an INSAT satellite will always be in the same direction, GSAT, or whichever satellite they are using for the DTH, and that antenna is oriented. Then, how do you express that orientation? In terms of the ground facilities, one is the elevation. That is, if it's vertical, you say elevation is 90 degrees. If it's towards the horizon, it's 0. So it's some angle between 0 to 90. The larger the elevation is better because you have very good look and the range vector is less. The other parameter is called azimuth, which says with respect to the local north, how much of angle you are away. From north to east is 90 degrees and south will be 180, etc. So by giving these two parameters, you give the direction, and then once you point in the direction, you get the signal. But unlike the geostationary satellites, normal LEOs and all that have a relative motion. When they have a relative motion, that means the red line which is shown here is the orbit. And if you look at the Earth, you can always find out which point on the Earth is vertically below the satellite. It's right this point. After some time, the satellite goes here, there will be another point. And therefore, you can keep mapping which is the sub-satellite point, that is, which is right below the satellite. That point is called sub-satellite point, and how it moves is shown as what's called the ground track. The ground track is useful to understand how it will be the coverage, and especially whether it will cover India or not. You can look at the ground trace. If it is over Africa, it may not have any way of reaching out to the Indian service at the time because the elevation will be less than 0, like that. So this is the idea of a ground track. For example, let me show you typical ground tracks. We have the ground track for, I have here typically given 1, 2, 3, 4, 5 ground tracks. One of them, the first one, has a period like 2.67 hours, and therefore it has a large motion like that you can see. Over that period, Earth would have rotated, and therefore, correspondingly, the ground track keeps moving across. The elevation, the inclination is taken as around 45 degrees. That's why 50 degrees. You see that it goes no more than 50 degrees north latitude, no, and here also 50 degrees south latitude, and it shows a sinusoidal kind of shape. But if the period is improved to 8 hours, then the amount of that rotation is different, and therefore you see the different curves. B and then C is there, 18 hours. If it's 24 hours, it's not at all moving. It's right where it is. If the inclination is 0, it will be a point. But if inclination not 0, it makes what's called a figure of 8. 50-degree inclination, 24 hours orbit will show a figure of 8 like this. This is how every day there will be. It's called geosynchronous, but not geostationary. So these types of ground tracks are there. And now, the last point before we go to a quick introduction to the mission area is to tell you that the coverage part of it, if you look at it, is basically how a satellite will be viewing something on the ground. It depends on what sensor is used, what is the field of view. Like here, this is called the field of view. And this is, let's say, 45 degrees. Then how much region it will be able to cover. This is important for remote sensing, for applications like that. And you notice that if you come to a larger height, then it gives you higher coverage. If you come closer, the coverage is less. That's understandable. So you get a more panoramic coverage when you go to a taller and taller point and then view. If you go to the top of a mountain and look down, you see Chamundi Hills, you go and you find, you can see the entire Mysore. That's because of the height. That is what is happening here. The higher the altitude, the larger is the coverage area. That's sufficient to understand. And the last point here in terms of the orbit related is what is called the orbit maneuver. Orbit maneuver means if there is an orbit, which I told you is forever the same because the initial conditions are same, and if there is no other force other than the Earth's pull, it will continue to be in the same path over and over and over and over again. But really speaking, there are some small other effects which are ignored. Those are called perturbations, which can also change the orbit. So initially, when you get the satellite, suppose that launcher orbit is not exactly what you want to make a correction, you have to know how to change from one orbit to another orbit. Such a change is called a maneuver, and that is done by using thrusters. In the next 2-3 days, my colleagues will be talking to you on the different subsystems. One of them would be talking about what's called propulsion, where use some kind of a chemical propulsion and you'll be able to produce a change in the orbit. The velocity is the initial condition I told you. If the velocity and position are the same, then the orbit is the same. But if the velocity is changed at the same position, instead of V1, you have V2 as the initial velocity, you have a different orbit. So the idea is to change the velocity by giving a small delta velocity using thrusters. This can be used for removing the injection errors, for maintaining the nominal orbit when there are perturbations. And then sometimes what happens in between, you want to do some change in the location or you deorbit it. All these things require a delta V maneuver where it can be in plane when you want to change only the period, or it can be out of plane delta V, which may even change the inclination. So if you want to change the plane of the orbit, you have to give delta V, which is perpendicular to the velocity. That's called out of plane. And in plane, you'll be able to change the period. You'll be able to change the semi-major axis or eccentricity. That is the idea of orbital maneuvers. At the last segment here, I want to move on to talk about the mission, how it evolves. Step by step, if a mission evolves. Mission is a word which all of you have now become familiar. Good old days, there was Mission Impossible and all that. Mission Mangal was one of those very popular movies. So you know that the mission means it is something which you want to achieve. Obviously, JNANAM is a very important mission which you are now undertaking. And what steps do you go over with this? The very first step is to do what's called the mission planning, where the mission requirements are obtained and they are derived by looking at the mission objectives. You translate the mission objectives to mission requirements. So then what you do, you analyze with respect to the mission objectives and arrive at and fine-tune the mission requirement. This is the iterative process. Please note, everything is very iterative, and therefore from objectives, because today we are at this level where JNANAM, we are talking about the objectives. Then to go into mission requirements, more details have to be written, and that goes through a few iterations like this. Then what happens? Then what happens is you have to derive the mission architecture. To mission architecture is again done by mission analysis. The architecture gives you details of what is the space segment, what is the satellite components, the subsystems, what are the orbits, other things, what launch system we'll use, and what are the ground segment, whether it is for controlling the satellites or for the purpose of getting the payload data, how the operations are to be controlled, and this design for the individual subsystems. All these would come up in the next stage, the mission operations, we call it. That tells you how the operations, which means the software elements, hardware elements, flight operations procedures, training, all those things, and what network should be used, where should be the payload data received, all those things, whether you want to have it in Noida or whether you want to share it with the ISRO station and collect it from a ground link, all those will be part of the discussions. So the next point which we'll talk about in the mission architecture is start from the broad objectives and constraints and start analyzing it. Okay, mission objectives are there, you start analyzing it and design this. You do lots of iterations. First you get a preliminary estimate of the mission needs and requirements and constraints, and go through another iteration. You'll get to finalizing it more and more. In fact, you should do what's called trade-off studies, where you put in alternate mission concepts. You should not freeze your mission requirements too early, because that time if you think that is the only goal, then you will be unnecessarily be violating some constraints of cost or schedule or maybe technology. So it will be better to keep some of the options open and then do the trade-offs and then decide what should be the right way to go. And the launch vehicle itself can pose certain constraints on, let's say, the volume, the shroud volume, its weight, then the orbit which is going to be delivered. All those have to be taken into account. And environmental effects, whether it is microgravity, ultra high vacuum, and all those things, particulate radiation, UV radiation, all these factors are very important while you take these into account. Once you have got the mission architecture arrived at, which I'm sure today my very next speaker, Dr. Jayakumar, is going to talk about in a specific context of JNANAM, is to go in and look at how the mission elements, which are so many of them, they're highly interconnected. The only reason of my showing you this is we are all going to work as a team. You may be working in software maybe, but still you should know what is the launch vehicle, what is space segment, what is orbit, what is attitude, what is ground segment. Not only for the purpose of telling somebody else, that bigger picture helps you to understand what is the role of this in the overall big scheme of things. And that is very important. The application decides the payload, and the payload in turn decides the orbit, attitude, bus systems, etc. Together, they will fix the launch vehicle, even the launch window, when it can be launched. All these are very important, because suppose you want to launch it for a polar mission, and then you should use the PSLV. At what time do you want to take the lift off? All these things. And the user segment, the TTNC, the telemetry command, ranging, all those kinds of things, mission control, all these have to be properly understood. You start from the user, you end up with the user. You try to give him something which is very, very exciting. And that is what we should do. We have a couple of minutes, maybe 10 minutes for question answers, because I know how vibrant this team was. I was very happy to see the kind of questions you people asked. Now this is the time to ask, and I will be available for most of the other lectures. If there's something to be added on or something to be coordinated, I'll be available. And thanks once again for giving me this opportunity. I'm very excited to be part of this team with a mission which is so unique, because I have been involved in missions for the last 45 years, but every mission is unique. But this time, when you're talking about some things can be done with 1.3 kgs or with such a small size and very useful data, is something which looks like a dream to me. Because when I first was the project director for one of the 150 kg satellites in ISRO, I was thinking 150 kg is not at all possible to do something useful like that, we are thinking. But now we are talking about 1% of that, and we are going to get more knowledge out of it, more jnanam out of it. Let jnanam be a big success. Thank you.
Thank you very much, sir.
Okay, I think I should stop sharing.
So
We'll now go for questions, because I wanted...
yeah, we can have it's informal discussion. Yeah. It's open for next anybody. 5 minutes at least.
Because it's supposed to be very interactive. Please note,
right.
The more you discuss, that is when you learn, and that's where we will also know where you are. Unless I know that, because we assume that people would have got this understood. But I'm sure that there are certain things which, because of the background, you may not have at all come across. I'm so happy that you have got some people who are from a pharmacy kind of background. I know how bad I am. If you give me one terminology from the pharmaceutical, I'll be floored in no time. So therefore, I know the reciprocal relation holds. So if you have not understood something, I'm not going to say, oh, you don't even know that kind of thing. It is something which I have to go and explain it to you, make you understand to the extent it's needed. See, you have to know the bigger picture correctly. What is what and how they all work together to achieve the goal.
So just to begin the conversation,
Yeah.
can you compare and contrast orbital motion of, let's say, International Space Station and a small satellite?
Okay. Basically, the orbital motion, as I was saying, is decided only by primarily the altitude. Because both of them are circular and they have a certain inclination. That doesn't matter here. So now it is only ISS for all that matters is another satellite. Only thing is a much bigger structure where it can accommodate so many people, so many experiments to do, etc. But its altitude is fixed in the sense that, whatever, I don't remember the thing offhand. I'm sure Jay Kumar will add to the correct number, maybe 400 kilometers like that, but they maintain it. Because unlike a satellite where by and large, we would not be wanting to spend too much of fuel, except for minor corrections, we would want to use the gravity to take us round and round forever. Here, we want to maintain that orbit. And for that, they carry additional propellant for maintenance of the orbit. And so it is exactly orbital motion wise, it is very similar to the satellite. That also shows how, when you are doing the biological experiments, you must understand, if you look at the ISS, for which there are extremely good videos of how people behave, because it's human beings, what are the constraints they have. When you have weightlessness, what exactly does it mean? That means that all the parts of every object there is all accelerating in the same manner. So there's no relative acceleration. So that's why you are able to just move from one to the top of that structure without any effort, because you don't need any other thing. There's no other pull or push. But same things will happen to a fluid or some other thing when you are thinking of an experiment inside JNANAM satellite. That would have mechanics very similar to what you will see in the ISS. Because orbital motion wise, it's very, very similar in a bigger structure like ISS to a very small satellite like ours. Because the mass gets out, when you write the equation, that second order ordinary differential vector differential equation, m, the mass of the satellite, immediately cancels. The force is gm like that. This side is m times the acceleration, m will cancel. So with the small mass or very, very big mass, the same mechanics. Moon has a very similar mechanics to whatever INSAT is similar to whatever Elon Musk's Starlink satellites.
Yes, thank you.
Yeah.
Yeah, good evening, sir.
Yes. Yeah.
Yes, sir. Actually, myself, Dr. Avinash Saxena, Assistant Professor, Department of Electrical Engineering, JSS Nevada.
Okay.
I just want to know this, sir, being an electrical engineer,
Yeah.
I have a specialization in the field of renewable energy, power system, power electronics, drive and control system.
Okay.
So how can I contribute for this project, in this project, sir?
Yeah. You see, basically, this project is something which is highly multidisciplinary. Your presence there, suppose somebody is designing the power system, your knowledge of familiarity with electrical systems in terms of storage, in terms of usage, in terms of regulation, all those things would definitely be useful here. And what happens is that the overall, that knowledge level, we have come across this, and you have over the years learned a lot of small things. They will come in handy only when there's a group discussion like that. Because this, I learned it about 45 years ago when I was becoming the director of Hassan facility. I found that there are 300 people with completely diverse skills. We were working as a team all the time. Every moment when we want to take a big new maneuver, new launch to a problem which has to be solved, to something which happens in the ground, we used to always collect people, maybe 10 people, and then we used to have brainstorming. And that produced very good results. So therefore, I'm very confident, Abhinav, that you would definitely contribute. It's not compartmentalized, because in a short period mission, you don't want to say that you do this, you allocate. You should be, as a team, will realize, oh, this part I will be able to do it, I'll solve and come back to you tomorrow. And one other team member can comment on that and say that, oh, this is very good, but I want to introduce another limit. Because as you get the data, you'll be able to interpret it very easily with your background.
Yes, sir. Thank you so much, sir.
Okay.
So I have one more question.
Yeah.
Is there any scope of clean and green energy, like sustainability and all, sir?
It's true, but everybody talks about green, including the RCB team yesterday came with a green kind of dress. Now, what happens is, yes, the space itself is something which is going to make things green. That's why in my slide you would have seen how to change the blue planet to green. And that's true that like energy, etc., which you are going to finally be able to channelize from a satellite to ground and all, will be much cleaner than what you produce on the earth. So the cleaner aspect will incidentally happen, but not in our mission. We will not be specifically looking for making something green and all that, because ours is very short, and we should focus on something which is a deliverable, which is very important for the community.
Thank you so much, sir.
Okay.
Good evening, sir.
Yeah.
Am I audible?
You are. Milan.
Yes, sir. So myself, Milan from EI department, JSS Mysore, sir.
Okay.
Sir, I just have a question. Once the satellite is in the orbit, can we vary the velocity?
Yeah. You can vary the velocity only when then that will change the orbit also, you must remember, because the velocity only decides the orbit. Velocity is changed. You change it by what's called the propulsion system. By changing the velocity, it's called delta velocity. That is, it has got already some velocity.
Yes,
you can add to the velocity, subtract the velocity, or change the direction of the velocity. Velocity being a vector is magnitude and direction. Magnitude can be increased, decreased, or change the direction. If it increase the magnitude, it will go to a higher orbit, in the sense that semi-major axis will increase. So wherever you fire the thruster, that point is a common point for old and new orbit. And so outward it will move to make it a bigger orbit. If you have a delta V, which is in plane, but opposite to the moving velocity, that means you reduce the velocity, then it will come inward. Okay.
Yes, sir.
Then if you fire out of plane, it will change the plane of the orbit. So you'll be able to change the inclination or the capital omega. So if you want to change the orbit only, you should change the velocity. Otherwise, you will leave it as it is.
Okay, sir. Thank you.
And sometimes automatically it happens, like drag. I didn't talk about the disturbances to the orbital motion. One of them is atmospheric drag at 500 kilometers or 600 kilometers orbit. That's very important. So you'll notice that over a period of time, suppose 1 year, it might have lost about 12 to 15 kilometers in the height. That is because the atmosphere is not zero, even at that height. It has small atmospheric density, maybe 10 to the power minus 13 meter per kg per meter cube, and therefore that would produce a kind of a drag, viscous drag. So it slows down the velocity, so it starts losing the height. It will make it circular, lose the height very slowly. That's
okay,
all.
sir. Thank you, sir.
Hello, sir. Am I audible?
Yeah, you are. Ankita.
Yes, sir. My name is Ankita from EI department, JSS STU Mysore. So my question is, what are the main sensors we are going to use in this project?
Yeah, of course, Dr. Jayakumar is going to talk next. He's going to give you an overview, and Dr. Parmeshwaran and Vijay will add more on very specifically what you use. But sensors are required. By sensors, what we mean is to know your orientation. Okay, so the attitude sensors, we call them. So it is something to know how the body is moving, all right. That is the orbit part of it, which we already discussed. The next one is the orientation of the object, because if the orientation is wrong, then the antenna will not be pointing in the direction towards the earth, and you may not be able to get the signal and so on. So you have to control the orientation. To control the orientation, just like in orbital motion, I told that there are forces which will affect it. For orientation, it's our torques, and these torques are disturbance torques, which can come because of so many. Magnetic storm can be there. It can be due to various other effects. It can have a tendency to rotate the object. It's called torque. A torque of that kind is to be first what it will produce? A change in its orientation, which has to be sensed. That is called the sensor. The sensor is with respect to a known object. Like it can be with respect to the Earth, it can be with respect to star, it can be with respect to a sun, etc., depending on the mission. At that point of time, you have a sensor which will tell you how it's oriented, and from that known present orientation, desired orientation can be reached by firing thrusters. So then you control it actively. That is the idea. So you need sensors, but for that you should know what are your requirements for orientation control.
Okay, sir. Thank you, sir.
Yes. Tyagaraja, you have a question? Please. You're not audible.
Mic is on.
Yeah.
Check your mic. No, the mic.
Hello?
You're not audible.
Yeah, Tyagaraja's, you're not audible. Are you muted? Yeah, now you're unmuted. Okay, go ahead. Why are we not listening? Unmuted, but still we are not able to listen to you. It gets muted all the time.
Not audible.
No, that's because it's shown muted. Can you unmute it, Sudarshan?
No.
Or you can unmute. No, we can't hear.
JNANAM, unmute your audio.
Can anybody hear?
Hello, sir. Now?
No, sir.
No,
No, sir. No, sir.
Okay.
he's not audible.
It's not audible, sir.
Okay.
Unmute your audio.
I think it's some
Increase the volume.
local problem.
Yes, sir. Now am I audible, sir?
Yes, you are.
Yes, yes.
Yeah. I was on the Bluetooth server. That's why it was not connecting. Sir. Fine, sir. So I understand that the satellite is of nano size, and I just want to pose this question: that the payload of the satellite and the problem we have taken and the fuel it carries, sir, how to relate this problem into the problem with which we are studying, sir?
Yeah, that is basically how you apportion the total mass into
Yeah.
the payload as well as for the different elements, including propulsion, which will be, of course, as part of the mass budget. Dr. Jaykumar will be touching upon this. So I'll leave it at that. And obviously, you have to do, see, there are a lot of budgets you have to do. Not only how the money is going to spend, that budget is, of course, Dr. Sudarshan will be taking good charge of that. Then you have to worry about what is the mass budget, what is the budget for the propellant, power budget. Everything is important, and we have to manage it all within those constraints.
Yeah. Yes, sir. Yes. Thank you.
Anybody from Noida? Last time there were lots of questions. Are there UT people also there from the pharmacy college?
I guess there are one or two.
Okay, all right.
Sir, my question is that can you suggest some books for the?
Oh yeah,
Yes.
not only that. I'm sure Sudarshan is going to. I don't want to break the ice. I will leave it to him to make the announcement.
Yes, we are working on supplying books.
Yeah. In fact,
very
we
shortly
wanted-
it will be in your colleges.
The idea was like this: during the process, which is only maybe 1 year, that kind of time frame, which is very short, you should have a reference kind of book. And one of the books which we have jointly written, that book is the kind of a very comprehensive for nanosatellites. We thought your library should be making available a book for each of you so that you borrow it over a long period, whether it's student or the faculty member, and then return it at the end of the mission. And that would help you to quickly check, because sometimes all this jargon is very killing. Suddenly somebody says attitude. I have never thought of attitude means, yes, his behavior, like that you are thinking. Suddenly here you are using it in the sense of orientation. That part of it, if you just glossary on the book will tell you immediately which chapter you should read and what. That's why we thought all of you should have this book. This is written for our type of audience. It's called Quintessence of the Nanosatellite. It's extremely well written book compiling all the ideas, and I think you should have a personal copy during the execution.
Okay. Thank you, sir. Thank you very much.
Yeah. Yeah, I shouldn't be eating too much into Dr. Jaykumar's time, but we are all one team. And therefore, that's why I said that, to move on smoothly.